Hello everyone, welcome. In this video let's solve problem 1 from LeetCode in APL. This problem is called TwoSum and someone requested that I solve it in the repository for the challenges, so here I am. Let's give it a go. So the problem says, given an array of integers, nums, and an integer, target, return indices of the two numbers such that they add up to targets. You may assume that each input would have exactly one solution and you may not use the same element twice. You can return the answer in any order. Alright, so what this says is that... so if this is the nums and this is the target, now the output here is 0, 1 because the element at index 0 and the element at index 1, when they are summed up, they add up to the target. Alright, and so how can we solve this? Well, the idea here is, or the thing I'm thinking of is that we could essentially the underlying algorithm here, like we can't be too smart, right? Because we have to look at the whole array and we have to do some kind of iterative search. And the only thing we can do is not look at the same pair of indices twice. But like there's not much in terms of the algorithm that we can use to improve it. So I think the obvious solution in APL is to get the vector defined and also the targets. And then what we do is, if we do an outer product with a vector, if we do an outer product sum with a vector, this produces all the, all the possible sums from, or all the possible sums you can get with elements from the vector. Now what you can do is, you can check which ones are equal to the target, and now you can use the primitive where to get the indices, and then you use a pick to get the first solution. Now the only thing I'm thinking of is, let's see, exactly, the only issue comes with examples like this. So here the vector, here the vector is 3, 2, 4, and the target is 6. Now if we do the same thing, the outer products plus will give us 6 in the diagonal. Why? Because 3 plus 3 is 6. And so when we do the pick of the where of the target equals the outer product, we get repeated indices. And this is not okay, because we can't use the same element twice. Or in other words, we should ignore the, the diagonal. So the way we can fix this is, let's see, or a way in which we can fix this is to how can we fix this? I mean, there's the obvious way would be to get an iota of the tally of the number of elements we have, and now we do another outer product, but this time we do an equals, with a commute, and this is the diagonal, and this is what we do not want to include, so we can negate this, or maybe easier would be to do an outer product with not equals, and now we want to use this mask to mask out the values that we can use. So let's take this. That's not what I mean. I mean and. Right, and so what this did was, let me show you again what this is. This is the Boolean matrix that tells me the places where two elements from the vector added up to the targets. And now what I'm doing is I'm ignoring the ones in the diagonal. So this one, when combined with this 0, will give a 0. And that's why we use the AND Boolean operator. And now we can do the same thing. We can pick where. and thus we get our response. So this is one possible solution. Let's see. Solution gets the peak of the where. Now this is where the masking out goes, so not equals. Can I please? What am I doing? Right. With the commute, now I ought to tell you of, let's say that the vector goes on the right, and alpha equals jot.plus with the vector itself. And so we do target sol vector. And this is the solution here, 1, 2. And we can try to see if this edge case also works. So the target is 6, the solution 3 by 3, and we get a 0, 1. Alright, so this is one possible way to do this. And now there's the follow-up question here, which is, can you come up with an algorithm that is less than n squared in time complexity? So this is n squared because we are literally computing a square of results, but essentially we are checking every single combination. How can we make this less than n squared? Oh wow, I have no idea. I mean, I know how to make it twice as efficient. Oh, I guess. Oh, I see. I'm just thinking out loud, but I think that to make this less than n squared, what you can do is you can sort the whole list, which is n log n, and then you can traverse the list from both ends. Oh, that's so much trouble. Yeah, the idea is you, let's see, the vector. You sort the vector, so it's 2, 3, 4. Let's make it a 7 here. Let's pretend that this is the vector, right? And now what you want to do is you want to start from the right and from the left. So you have like 2 pointers and you see, okay, what does this add up to with this? And it adds up to 9, which is more than the target. And so because this is too much, what you do is you reduce the right counter. Now what does this add up to? 2 plus 4, it adds up to 6. Okay, this was the target. But say that the target was 7. And you start like this. The pointers are pointing to 2 and 7, so this adds up to 9. Too much, so you decrease the right pointer. 2 plus 4 is 6, is too less, or too little. Too little, not too less, sorry. And then you increase the left pointer. Now 3 plus 4 is 7. Okay, great. And so you can find a solution like this, and this is, yeah, this is n log n. Yeah, but I'll do this. I'll try to do this n log n solution in a separate video. So for this video, the solution we have is n squared and just uses an outer product, or rather 2 outer products. See you soon. Bye.